to give you a little CV of Kelly. So Kelly is a research associate for the BCIT Smart Department, and his department has been focused on smart microgrid solutions for the last decade to help remote communities reduce their reliance on fossil fuels. Electric cars and battery storage systems will play a huge role in balancing that. But Kelly has been focused on the hardware and software integration of the EV charging infrastructure. And he has his department has purchased and installed 6 DC fast chargers. But what he's going to talk to us about tonight, which is really important to all of us, is helping us to get EV charging into condos. And so he'll be talking about his latest project, which is the design and installation of energy management systems to facilitate EV charging in condos. And Kelly, you can correct me, but I think I've got that pretty well correct. Is that right?
Yeah, that's right.
Yep. And so what I'll do, Kelly, is I'm just going to hand the meeting over to you and you take over. And if the rest of us can mute ourselves, that would be great.
Okay, so I should be able to see my screen now. Yeah, so for the last decade, we've been working on EV charging, and starting in 2014, we installed Oasis at BCIT, which is a 250 kilowatt solar array, along with 500 kilowatt hours of lithium batteries and 2 DC fast chargers that ran off the power from that big battery and the solar system. And we wanted to see how we could integrate all these things together and make it work better for remote communities. And so during that time, we've learned a lot. We found that a lot of the software and hardware wasn't available at the time. And so we had to create everything from scratch, basically at the beginning. So we had to make a OCPP ecosystem, which is like an OCPP server, which is what Greenlots and Switch and Charge Labs, that's what they have created for their own businesses. And we also had to create our own OCPP client, which is what would go inside of a charging station. And because the charging stations at the time did not have OCPP, but everyone was talking that it was coming and it was going to be a really great thing. The DC fast chargers had been deployed with an earlier version of OCPP, version 1.5. And it was causing a lot of problems, and so we needed to see how these things would work when it was all put together. We also had to create an administration tool to allow people to set up and add charging stations, see what was going on, getting all the reports from the charging stations. We also had to create our own user app, which is just like ChargePoint or Add Energy Stations app, which will let you bring up a map of the charging stations and navigate to them, see if they're busy, whether they're available, whether they're faulted, broken in some way. It would come up as a red icon. And for the administration panel, we would be able to see that at a glance through a dashboard. We'd also had to create an OpenADR Venn integration to our system so that the utilities could control the charging stations. We also created an OCPI roaming software so that we can connect to companies like ChargePoint and Add Energy Flow to be able to share user information so that if you had a Flow charging account, you could come to BCIT and tap that card at our stations, and we would accept it and collect the money through your account on Flow. We haven't done any peering arrangements yet, but it's all set up. So we had to create all that stuff first before we could really do a whole lot. So once we started down this path, we had to create our own charging station. So in our situation, we create a thing called a local controller, and it would talk to the Sun Country charging stations that we found we could control through a serial protocol. And then we hooked it up to the Ethernet through a serial to Ethernet adapter. And we had a little Linux box that we run our software on that would control the chargers and speak over the internet to our OCPP server. And so as far as anyone was concerned, that was a normal EV charging station that was smart. And so the one little computer that we were using can control hundreds of EVSEs in a building. And so then we get into what we actually came to talk about, which is having an energy managed system for a building. And so at BCIT Oasis, we had enough power for about 5 charging stations, a little over 5. We had a breaker panel that had 140 amp main breaker in it, which means through the calculations I've shown, it's only about 40 kilowatts of charging for level 2. And what we wanted to do is install 10 level 2 chargers. And we have 2 120 volt outlets with a NEMA 520 plug. So it's like a plug that's in your kitchen. And that's 70 kilowatts of load. So we've definitely way overloaded our panel. So we had to control the charging rates of the cars so that we would never exceed the 40 kilowatts. Overall, there's also limits on each line because it's a 3-phase system. So it's 112 amps per line in the panel that we also have to limit. So in a energy managed system, we have what we call uncontrolled base loads. And these are loads on the system that we haven't monitored and we can't control them. So if we have a 110 outlet, anyone can come along and plug anything into that 110 outlet and get power out of it. So you can plug in a level 1 charger and it might draw 14 or 15 amps, maybe up to 16 amps if it's in the NEMA 520 connector. And so we have to assume it's being used all the time, or we have to monitor it. And that's the next step, is if we add electrical meters onto this system, we can monitor the power that this outlet is using at any time. And so that will allow us to use that power that we would normally had to have reserved for that plug. And now we can use it when no one's using that 110 plug. And then when someone does plug in, we have to turn down the EV chargers to make room for that new load. And so when we're going through all this stuff, we looked at it and said, well, we've talked to a bunch of different people that were trying to do this. And the way that they tried to do it seemed really convoluted to me and meant that they would say, oh, these 2 chargers have a limit of 5 kilowatts together, and these other ones have 5 kilowatts, and all together they have 7 kilowatts. And the bigger that it got, the more opportunity there was for someone to forget one of the settings and groupings, and would cause failures because it got really complicated very quickly to manage. So we looked at it and took a step back and said, well, why don't we model all these different components? And when we're modeling it, we'll understand what attributes we have and what things we can control and stuff like that. And so we started with what is an EV as far as an EV charging model. And so we know that an electric vehicle has a capacity of the battery for traction. So we know it has like a 24 kilowatt hour battery or 100 kilowatt hour battery. We know that some cars can only charge at 16 amps, some only at 12 amps. Most EVs today now charge at 32 amps. Some Teslas will charge at higher rates. Different new vehicles might charge at higher rates than 32 amps. So we keep track of all this kind of information, what type of connectors they use, if it's AC only, or whether they use a CHAdeMO connector for DC or an SAE combo connector for DC. We also had to come up with a list of defects that each car had for charging. And one example was Tesla had some defects that we were trying to work through and figure out exactly what caused the Tesla to not charge very well on the system. And so we would try to work around those bugs. So we also noticed that slow charging vehicles may want to get higher priority when charging, because if they kind of fall behind, they can't catch up as easily as a car that can charge faster. So some vehicles refuse to restart when the EVSE is paused for any length of time. They may also get priority to ensure that we don't try to pause them instead of a different vehicle that would restart properly, because it would be very annoying to someone start charging a vehicle and an hour the system paused charging on their car, and then they get a notice 20 minutes later saying their car stopped charging and it went to sleep and would not start even though the EVSE was offering power again. We also know that the driver using the car may want priority charging at some point. That is a little bit more complicated to get feedback into the system, but we do have the facilities implemented in the model to deal with that. Then we looked at the level 2 EVSEs, and there is a bunch of negotiation that goes on when you plug a J1772 into a car and both are turned on. The EVSE will tell the car how many amps of power that are available to use, and the vehicle will report that it is connected and whether or not it wants any power at the moment. So we control the pilot signal to change how many amps that we want to advertise to the vehicle. So with the Sun Country chargers that we use mostly, they're all like the standard 40 amp EVSE, which can offer up to 32 amps of power. And we can set it to offer no power, 8 amps, or 16 amps, or 24 amps, or 32 amps. So basically in 25% increments of its maximum power. And they have chargers that up to 80 amps, and they are proportionate. So they would do 25, 50, 75, and 100% of that power. So when we get into looking more at what's happening in the building, we look at what does a breaker do? And basically the breaker is there to protect the wire. We know that that's physically what it's there to do. In the software world, I'm trying to make sure that that breaker never trips. And so we know that a 40 amp breaker normally is they listed as being a 2-pole 80% 40 amp breaker, which breaks down to meaning that it takes 2 lines in. It can operate at 80% of 40 amps continuously, and which means 32 amps. And so that's how we know that we can offer up to 32 amps, and we don't have to worry about that tripping the breaker as long as the breaker is not old and defective. So in this example, this picture I showed, we have 4 EVSEs. We can put all 4 of these EVSEs behind a single 40 amp breaker, and we can offer 8 amps to each car if all 4 were in use. We could put 6 chargers behind this 40 amp breaker as well. But with these chargers, with a minimum of 8 amps, it would mean that only 4 could be getting power at a time. And so it's not impossible to have 6, but you start having to shuffle power around, saying, turn these two off for the next hour, and then turn those on, turn 2 others off for the next hour. And so you end up shuffling through the things. And I would prefer not to do that. I know Don Chandler has been a big proponent of going up to 6 if that's all the power requirements people have. And we haven't gone down that road to really see that in action yet. So then we looked at the electrical panel, and Don was a big help on this. What we've decided to do is model electrical panels in the building and we tell the system that we define a panel. This one that I have up on the screen is called lot 7 because that's in the parking lot 7 in BCIT. And we're showing a pseudo panel schedule, which shows what charging stations are connected to which breakers in the panel. And someone could print this out and put it next to the panel and verify that the electricians have done their job correctly and installed all the breakers in the right location. Because when we look at the charging stations, we actually need to know that like level 2 charger number 5 is on phases C and A, and it's behind a specific breaker, so we understand what limits we need to impose on the infrastructure. Then we really get into energy and power monitoring. And so the picture here is again a breaker panel, and on the right-hand side you can see all these things we call, well, they're called CTs and our current transformers, and they look like a donut, and they clamp over top of the wires going to the charging stations or to the loads. And they have some wires running out of them that go to the actual energy meter. And that energy meter will keep track of a bunch of measurements. The ones that we found that we were using were volts, watts, watt hours, amps, and VAs or KVAs, which are very similar to watts, and we won't need to get into the difference, but they're very similar to what the watts are. Now, it's important to understand that these energy meters that are installed in this manner, they can be revenue grade meters approved by Measurement Canada. You buy the right current transformers and you buy the right meters, and then you get them certified and sealed to ensure that they're accurate when they were sealed. And you would now be able to bill by the kilowatt hour using these measurements because Measurement Canada has approved the metering. So this other part of the screen, we have the energy power, the site energy meter lot 7 EM 4805, which is a big long technical term for the specific meter that we use. And we lay out which meter point measures what power in the electrical panel. So now we start to get complicated because we can stack these model components together into I call it an org chart. It's the organization of all these components. We also call it a tree diagram. But if we look at the very bottom, we'll kind of work our way up. And so we have a EV at the bottom, and this EV has a 32 amp maximum charge rate. And so through the software, we tell the system this car can charge at 32 amps, which we tell the EVSE that this car can only charge at 32 amps. So we will never offer this car more than 32 amps. So if it can only charge at 16, we'll only offer it up to 16 amps. And currently, this picture shows that we are offering the car 32 amps out of the 32 amps that are possible to send to this car. This EVSE reports up to the virtual breaker, saying that we're using 32 amps of a pilot signal from the EVSE to the car. And so the breaker now knows, oh, 32 amps are being used, and this breaker is a 40 amp breaker, so it's allowed to use 32 amps. So we are 100% full of what has been allocated. The breaker then reports up to the meter point and is saying that we're using 32 amps. And because the breaker is on phases CA, it reports that up to this meter point. This meter point will read the actual consumption of the charging car. and it's saying, you said it was up 32 amps, but this car is actually only taking 27.8 amps. So that's 87% full. Yeah, so then reporting up from that meter point, we were reporting 27.8 and no longer that it's 32 amps. So we can start to get back some of the extra power that we're not actually using in the car charging. So we also do this for the uncontrolled loads. We said we had two 120 volt outlets, and so they're not being used. The breaker says that there's nothing being used. They passes that up to the meter. The meter reads it and says, you're right, there's no power being used. And that takes care of the uncontrolled load. So at BCIT, like I said, we had 10 EV chargers and two 110 outlets. This is what our design software shows as our tree diagram of that setup. And so at the bottom, we have all the charging stations where it's labeled Oasis L2:8, L2:5. So these are all the charging stations. And it shows that level 2, number 8 is connected to a breaker that's 40 amps. And we have the label for the breaker. It's in slot number 12 in that panel. And above that is an electrical meter. And so we measure that, and then all of these meters report up to what we're calling lot 7-0, which is the main breaker for that electrical panel, and it's a 140 amp breaker. And above that, we have another meter, which is measuring the consumption of the entire panel, and it also doubles as a way to do protection on the upstream transformer. So transformers use the kVA measurement, and so that's what they're rated in. So we can put a limit at this meter point saying the upstream transformer is, say it's a 75 kVA. We would want to put a limit in kVA somewhat less than 75 kVA, and we will protect that. We will prevent more power than 75 kVA to be used by the EV chargers. Now, so that was the engineering view, and then on runtime, so this came off of our local controller that was actually doing the function. And so at this time when I took this snapshot, you can see there's lots of all the cars are busy charging. They're not all taking 32, and they're limited to something less than 32 amps. There's nothing on the two 120 volt outlets. But when we look up at lot 7-0, it says it's 95% full. So we've done a pretty good job of maximizing the power that's available in that panel. And our kVA limit was at 90%. And above that, we have this thing, we call it the OCPP limit. The server can actually send down new limits at any time. And that's why we would hook into things like a utility, so the BC Hydro could tell us that, yes, you normally allow 300 amps of charging, but can you reduce it down to 200 amps for the next 4 hours? And we will pay you for that, is usually the reasoning why the building would want to slow it down to 200 amps. So that was all done from the local controller's point of view. So with a little computer inside the building that's keeping track of all these charging stations, and these changes can happen very quickly. But it's also very complicated. And so we tried to figure out how we can make it much easier to deal with. And so we looked at moving, instead of controlling it at the charging station at the controller, can we do it from the OCPP server? And I was very dubious about it at first. I was really scared that we were going to start tripping breakers. And Matthew Luce was a great help on this at coming up with an idea that would allow us to do this. And so moving it to the cloud, we're not stuck with using just Clipper Creek chargers anymore. We can use anybody's OCPP chargers as long as they support a full set of the commands that OCPP 1.6 makes available. And that would make a lot of people happy, because now you can use the light on or the ABB or the EV box, and you can mix and match. So you don't need to have everybody's EV charger in the parking lot the same brand. Maybe they don't like the light on product, or the VersaCharge might be too expensive, and so everyone could buy their own charger and we could connect it to the system. So moving it to the cloud, we lose all of our meter lines that we saw in the previous diagrams. The energy metering would come from the chargers themselves, reporting up to the breaker, but there's no meter above it. So if we allocated 32 amps, we would assume that 32 amps was actually being used all the way up. So there would be some losses there. And the 110 outlets or the 120 outlets, we would assume they were always being used. So we would notch out the 16 amps for each of those 120 volt outlets. So that's the downside to going to the cloud, but this configuration is much easier and can be changed on the fly. And so here is a view of the Oasis system running as a cloud EVMS. And so we were able to see how much power it allocated to each EVSE, and it got up to, and the lot 7.0 breaker, it's reporting that it was using 110 of the 112 amps available on line A or line 1, 97 on line 2, and 97 on the line 3, which means there was room for some EVSE to use more. But at this time, there was a couple EVSEs that nobody was using, and the chargers that were in use were not on B, C phases, so we couldn't turn anybody up to take advantage of those. Most of the people that could use the power were using line 1 at some point, and there was only 2 amps available on line 1. So it's not just been at BCIT, we've actually done a real deployment now at Riverbend in New Westminster, where we have about 100 parking stalls. We've only installed the first 6, but we've designed it using AES engineering to design the entire parking lot. And what we would do, and all the components we put in were based on 100% utilization. And so they would just add in the additional components, but we installed a very big breaker in the electrical room, and then the conduit sizes were appropriate for completing the entire parkade. And in this case, if we start at the top, what we've done, if we have a 300 kVA transformer in the electrical room, and we monitor that with a Dent electrical meter, and we can see on the side here, this is the actual consumption from yesterday for a 24-hour period. And so once these EV chargers start to use a lot of power, they will start to fill in the valley here and overnight charging. And we have the peak at dinner time, and there's definitely enough power without us ever raising the peak power consumption of this building. We will monitor the transformer to make sure it never gets exceeded its kVA limit. We have our local controller in the electrical room, and a 600 amp breaker feeding basically 100 EVSEs. And so we set up 3 panels. The first panel, which was the one that we've actually deployed, is called EVC, and it has a 225 amp breaker for the main breaker on that panel. And there's room for 32 EVSEs. And we have our Dent meter measuring all the consumption. So if Riverbend wants to charge by the kilowatt hour. Everything is there to make it revenue grade. They would just need to go get the meter certified, sealed and certified, and they would be billing by the kilowatt hour, which everyone keeps saying can't be done. It's not possible. We also have the OCPP cloud for billing. And so BCIT, of course, had built the OCPP cloud so that they could connect to. And here is the real parkade, where we have our electrical panel, our metering system, and on the very left is a comms closet, so we can put switches. We do not use wireless in any of this. It's all run over Ethernet. And this pipe coming up here along the roof, there's a datacom closet in the building directly above this parking stall. And so we drilled through the floor and got internet directly from the building's internet connection. So there's no cellular bill, no Wi-Fi issues, and should be a rock solid system for many years. And so we have 6 EVSEs mounted on the wall, and we have one left that we've left kind of wired so that they can add 2 more because of the conduits were already going past there. So there was no point running conduit and not putting in the stubs for the EVs, the EV chargers. So that's not the only architect that we looked at when we were designing all these systems. There's another really common architecture, which is townhome complexes. And this shows one of the ones that we looked at. And they had 3 different pad mounted transformers because they had many buildings on the complex. And each pad mounted transformer would feed a meter stack closet like we see here. And there's 16 individual meters here, 1 for each homeowner, each townhome. And each one of these meters would then feed a 100 amp panel in the townhome in the garage. So that was very convenient to be able to add in another 40 amp EVSE into that 100 amp panel. But you're very likely overloading that 100 amp panel because you already have a 50 amp stove connection and a 30 amp dryer, and you have a bunch of lights and plugs, and some people already have air conditioners. And so you're probably overloading that 100 amp panel by just putting in a standard 40 amp EVSE. And if you're not overloading it, you're probably going to overload this pad mounted transformer and the electrical infrastructure between the transformer and the meter stack closet. And so this was another great example of how we could use this technology to solve these problems. So we could install internet connections throughout the system using power line communications. And we would have one EV EMS computer and one of the DENT meters installed in the meter stack closet. And we would then monitor everybody's load, just like BC Hydro's doing. And we would be able to protect the pad mounted transformer. And we could put up to 2 EVSEs in everybody's 2-car garage and offer up to 32 amps across these 2 EVSEs. And so we haven't gone down this road of actually doing this yet, but it's coming up a lot. And this is probably one of the areas that the energy managed solutions are going to be quite popular. So part of the software side of things that we built. So we had to make this entire management software. So we have a dashboard where we can configure and manage equipment, troubleshoot issues, roaming with OCPI, utility integration with OpenADR. We do emissions reporting, which is going to be very common for people trying to collect the carbon credits, since condos are now going to be capable of recovering the carbon credits, and I think that'll make a lot of people able to install EV charging in condos. It'll also take care of tariffs, which are a fancy way of saying the billing rates for EV charging. There's the customer billing components, and of course the energy management in the cloud all gets managed from this software. So we also have a user like the EV driver portal, and this is where you go in and you say, I want to charge my car, and it'll show you all your previous charging sessions. You can make payments through Stripe to pay for your charging. So we have our environmental impact and energy sources, and this is updated, and usually it's annually, the information that we get from BC Hydro for their annual reports of what their carbon and intensities are for their mix. At BCIT, we have a huge solar array, so 71% of our energy was being generated from solar, and then most of the rest was all BC Hydro energy mix. And we can see how many kilograms of CO2 were generated. Yeah. So one of the things that I thought was important for condo people especially is the idea of a monthly subscription fee. Everyone keeps talking about how much it costs per hour to charge, and really, you know, if everyone said, oh, it's going to cost about $30 a month for everyone to charge, if you just put a subscription fee of $30 a month for the EV chargers, then the drivers could pay via credit card on Stripe or other ways, and it would automatically let them charge. And if you didn't belong to the membership subscription, maybe you would then charge $2 an hour to use the system, which is where we have tariffs. And tariffs are really interesting because they're very complicated, but they still don't do all the things that people would like them to. This tariff structure is actually defined by OCPI, so everyone has to kind of follow this tariff structure of how the tariff information is stored so that they can share it with peers. So if BC Hydro customer goes and use a charge point station, they have to be able to share the billing information in a format that everyone understands and is going to calculate the same cost, whether it's BC Hydro calculating the cost or whether it's ChargePoint calculating the cost. And that's one of the issues that people complain about, is that when they go to Electrify Canada and their car used 73 kilowatts for 10 seconds, it gets recorded that that was their peak charging rate. And the tariff for that whole session is based on that 10-second peak that they had. And there's not much that Electrify Canada can do to solve that, because they said if you're over 70 kilowatts, here is the price for the entire charging session. So it's kind of nice that they can do roaming and sharing this information, but we all know that what we really wanted was if you're over 70 kilowatts, maybe you got billed at that rate for one time period. Maybe that's 2 minutes or a 5-minute period of that premium price. And then when your car was actually charging at 50 kilowatts for the most of the time, that's the tariff rate that was used for that session. The components that they can actually charge you for is you pay by the kilowatt hour or by the session, and these can all be combined. So you can say it's $3 per session plus 10 cents a kilowatt hour. And then they have how much idle time. So if you stayed after your car finished charging, how much would you get charged? And we have this thing at the end called step size. And so that is interesting because you can say charging by the hour for idle is based on, you could say it's 15 minutes. So if you're there for 1 minute, they'll charge you for 15 minutes of parking. And then if you stay for 16 minutes, they would charge you for a second step size of 15 minutes. So you get charged for 30 minutes of parking, all depending on how the parking people want. Because one of the things I've learned is parking people really love breakage. They want to charge you for an hour worth of parking, whether you're there for 10 minutes or the whole hour. They would love it for you to park for 10 minutes, pay for an hour, and then leave, and then someone else can come and pay for an hour for the exact same stall. So that's why they have this step size thing in here. So when it comes to collecting money, the EV drivers can log into their app or the website, and they can enter their credit card information and pay through Stripe, and the money will go into the into the network operator's account. And so if it's the Strata that's running the system, it would end up directly in the Strata's merchant account. Otherwise, the network operator would transfer money as it's earned. So like if you had a subscription fee, when you charged all your customers their subscription fee, that money would then get transferred to the Strata's account directly. And that would save a lot of time for people not wanting to manage it. And if the balances go below zero, the customers wouldn't be able to charge anymore until they updated their balance, and then it would be allowed to charge immediately again. So the other concept that was important for condos was usage limits. So maybe if your subscription fee was $20 a month, you wanted to say that, yes, it's $20 a month, but you're allowed 4 hours a day to be charging if it's in a shared stall. So that, and then if they stayed there for all day, the next day they wouldn't be able to charge, or whatever limits you set up. You said if it was 4 hours a day or 20 hours a week, and then if they stayed parked for 20 hours and not moved, it would annoy a bunch of people, but the next day they wouldn't be able to charge at all again. So you can control these in the system as well. So other systems that are interesting and may not be perfect, but they have a place to live. It's like there is the DCC EV-EMS, and the way it works is that it measures all the power on the electrical panel. So in this idea of the townhomes, what you would do is on these 100-amp panels, you would install this DCC 12, and it would watch to see if you're overloading your panel, and if you are, it would turn off the EV charger. And then after the power went back down below a certain threshold, it would wait like 10 minutes and then turn the charger back on, allowing the car to charge again. And I look at it, it's really a safety system. If your panel is actually overloaded, this is a horrible idea, because your EV charger would be powered off all the time. Your car might not like it too much either, having the charger being powered on and off all the time. So it really is a safety system to ensure that you're not overloading your panel. And so Ron had shared this with me a couple days ago about the Evolute, and I see systems like this all the time. There's been many that have popped up in the last 10 years doing the exact same thing. And so it's basically a smart panel. And what a smart panel is that it looks a lot like the infrastructure that I was showing you at the beginning, where we had the panel, the electrical panel, and it has contactors built into this thing that would open and close, and metering, so they would know how much energy each car had used. But it's really designed for 1 EVSE per breaker, and I think they were using these for what do they call it, the block heaters. So they would turn the block heater on for half an hour, and then turn those block heaters off and move to the next batch of block heaters and run them for half an hour. And so that's kind of where this technology was used. And lighting, outside lighting circuits, they would have similar systems as this. And this example I pulled up, it was 600 amps, just like what we did for 100 and a few EV chargers in Riverbend. these people do 30 EVSEs with that same amount of power. So as I left this thing open, like smart panels are, and they really are a dumb idea for EV charging. So there's a lot of drawbacks that people don't think about. They try to say that these work with any EVSE, and technically it's kind of true, but the vehicles like mine, my Leaf will go into alarm if the EVSE powers off more than twice in a charging session. So I'll hop in and I'll have a big red triangle on my dash, and I'll have to move 10 feet, turn it off, turn it back on to clear that red triangle. The EVSE and the vehicle have contactors in them that open and close. So these are moving parts, and the contactors in most EVSEs are designed for a rating of about 10,000 cycles before they start to fail. So you really don't want to be opening and closing these contactors every 30 minutes just for the sake of switching to the next EVSE to charge. Smart EVSEs, when they're powering down, they will probably write their configuration out to an NVRAM to make sure that their state information is correct when they boot up the next time. And if you've ever had an old car with a digital radio, they eventually wear out and your preset radio stations don't work anymore. Well, that's what's going to happen with these EVSEs if you keep power cycling them all the time. I know I wouldn't want my computer plugged into one of these things and having it rebooted every half hour until the operating system came up with an error saying that the file system error fix me. The smart EVSEs will also be reporting every time it reboots to the network provider. And normally this is a really good indicator of whether or not there's hardware errors happening with the station, so that they can let you know that the EVSE install 45 it looks like it's failing. Do you want us to send you a new one? With these reboots happening all the time, you kind of defeat that whole possibility of them looking at the number of reboots that the stations are having. The vehicle will send charging stop notifications to the driver, so you would have to turn that feature off on your vehicle if you're using one of these systems. It also isn't compatible with EVSEs that require you to tap to start a charge, because you would power cycle the charger and it would come back up and it would say, okay, there's no session anymore, come back and tap your card again. Which, and even worse, when you show up and plug in, that EVSE might not even be powered up at the time for you to tap. You'd have to try to catch it while it was powered on. So the EVSE certifications that I've seen require the EVSE not to start immediately after a power outage if a vehicle was connected when it was powered up. So normally this is a delay of 2 to 12 minutes. So, and that's to protect the grid. So if the grid did have a power failure and now you're trying to start up and all these cars want to put huge loads on the grid immediately, that's not really desirable. And that's it. I bet there's a ton of questions and stuff, and I know I went through a lot of this stuff very briefly because I probably have 200 pages of stuff I could go through.
That's great, Kelly. If you could just stop sharing your screen so that I can see the people that are attending. And if you want to ask Kelly a question, use the hands up feature. So if you go to reactions and you can put, if there's you just hit raise hand. That way you'll come up to the top left-hand corner and I'll be able to see you and get everybody in sequence. And the first one that raised her hand was Karen Kavanaugh. Go ahead, Karen.
Kelly, that's great description of that system I've seen over there at BCIT. It's quite impressive. And what I'm missing a little bit is it sounds like you've developed something that's rather unique, or is that the case? Are you propagating these systems successfully somehow, or what does BCIT plan to do to get more people to set these things up?
So that's a great question. So what we're doing is this entire ecosystem that I'm talking about is becoming open, is open source, so people can download it and run it themselves. We also have partners that are actively getting ready to start shipping this. So obviously Sun Country will have their solution that's specifically designed for Sun Country. There are many other companies around BC that are doing it, and around the world that are waiting for us to release this code, because we haven't actually, this code that we're running right now, we're still in testing, and by the end of December we'll have a full release available for people to run. We're also going to be releasing to like Switch and Charge Labs and other EVSE network providers. Not just the software, but more of a, here's all the interfaces that allow you to do this, so they can quickly implement systems like this without having to go through the R&D that we did.
That answer your question, Karen?
Yeah, it's like a combination of private and public. Is that how you would describe it? I mean, you have open source, so anyone can start applying it to their own setup, and as well as the hardware.
Yeah, so there's hardware. The hardware component is being made available to Sun Country as a project partner, and so they have this extra magic version that can do all the energy meter readings on site and local controller. The rest of the world will get the cloud version.
Okay.
Good. I don't see any
I
more hands.
need to also, I see Mike Schuler's there, so I really need to let people know that Mike Schuler, he's just like the king of this, and he's the one who's been doing this the longest. And I don't want to spoil any of his thunder about his product, so I've not put any of his product stuff up yet. So if he wants to talk about it, I would give him 5 minutes to at least tell us if he's ready to tell us what he's working, what his new stuff that he's working on.
Mike, would you like
No,
5 minutes?
I don't really want to talk about variable grid, Kelly. What I was interested in is how you would make available. Is there a modular approach to your software in the sense that, let's say somebody had let's say they had an OCPP server and they wanted to integrate utility control into it, so that the utilities would actually take them seriously. Is not just a clown that's running around with his own software, but actually can integrate into OpenADR. Is that possible?
Yeah, totally. We have our OpenADR VEN, and it currently is integrating in through SQL database is what it's updating and managing. And so all you need to do is connect to that, either update what database it's connecting to and how to, and hooking it to something else, or connecting to a database and being able to read what it's currently storing.
Oh, so some of those database fields would be read only or write only, from depending on whose point of view.
Right.
Okay. Yeah, okay. Yeah, all right. Well, I'll take a look at that. That would be very interesting. Yeah, I know we're working on a variation of variable grid that people are going to find interesting. Greg is working with me on that in Toronto. So, but I can't talk too much about that right now because similar to your position, we're in the final testing stages. So, you don't really want to talk about something that may actually go the wrong way when you start seriously testing. But okay, no, that was an interesting feature that might be applicable. Okay.
Okay. If I could ask Kelly a question. There's several acronyms that you were using, and I wonder if you could just define some of them for some of us who are just a little less up on it. I know what OCPP is, but maybe you could just tell everybody what that is.
So OCPP is the Open Charge Point Protocol. It's the de facto standard of communications between charging stations and the network provider that provides billing and services to those charging stations.
Right. And there's another term, the ADR. That's one I'm not familiar with. What would that be?
So yeah, there's Open ADR, which is the Open Automated Demand Response, which was developed in California. And so let me explain what types of information the utility would send. And so the utility can send out a message to people that are subscribed to these messages, and they can send out the message with a geofence around where that message is supposed to go to, so it can target specific neighborhoods or the entire province. And the messages will say something like, in 12 hours from now, I want you to move to stage 3 energy management. So they usually have an energy level or energy management level of 0 through 4. And 0 is usually representing saying there's no energy management, do what you normally would do. 1 is a little bit of energy management, 2 is more energy management, 3 is more energy management, 4 is as much as you can, obviously. Or they will send a price signal that says electricity is normally 10 cents a kilowatt hour, and for the next 10 hours, it's going to be 25 cents a kilowatt hour because we're really short on energy. So those are the kinds of messages. And so we built that into saying, if the price is over 20 cents, here's the energy management that we want to do to the EV chargers, like turn them way down if it's really expensive.
So total control of that. It's just, yeah, incredible. And of course,
so just to say, so it's
sure.
The utility doesn't tell us how we're supposed to react to it, like how much energy management. They just kind of give us these kind of indicators of what we should do. So we still have to tell it what 25% means, right?
Yeah, so you have to say to it, oh yes, if we're at energy management level 3, we can just carry on doing nothing. Or if we want to save ourselves money, or like if the hydro rates are going to go up to 20 cents a kilowatt hour, we have the option of trying to save ourselves money or not as we choose.
Yeah.
Yeah. And the other one, SQL Server Database. Maybe you can just give a real quick explanation of that if you could.
Yeah, so a SQL database is if people know what a computer database is, that is SQL is a specific type of database with you can interact with them with pseudo English kind of commands to it. Think of it that way versus really cryptic.
So you don't have to know DBase and know all the dot commands and all that kind of stuff. You can sort of use English.
Yeah, it's a pseudo English. It is structured, but yeah. I wouldn't say it's a user thing, but it's a programmer thing that makes it easy, so you can move between different databases very easily.
Right on. And I don't see other hands, so I'm going to ask one of my questions. I didn't know about Strata's being able to trade the carbon credits. Can you tell me a little bit more about that?
Yeah.
Maybe Don Chandler can talk about that. I think he's the most up on that.
Sure, I can mention a little bit about it. The province in late August announced or resolved the debate that was going on about who gets to collect the money for carbon credits. It used to be just the utility would qualify. And then they were thinking maybe the service providers, the charge points, Ad Energies of the world, could collect it because they control a lot of the groups of chargers. But the decision was to let Stratas collect it. So if you're a Strata and have 100 cars in your parking lot, and they're all charging and maybe $30 a day as average usage, then they would be able to get the carbon credit for which they can trade on the open market. And at today's carbon trading price, that might average anywhere from $200 to $1,000 a month for typical Strata users. The Strata would collect that money and then put it into the maintenance budget for fixing the roof or whatever they want to do with it, maybe return it to the EV owners. But that puts the money back in the pockets of the people who are supporting this, which is a big change and almost covers the cost of your electricity for your charging, making it free to drive an electric vehicle. Some of my calculations, when I look at how much power people need, I also calculate if everybody were driving, how much they get returned on that. And it depends on how far you drive, of course. The more you drive, the more you get.
If I could just step in a little bit, just to add on what Don is saying, this is all because in British Columbia, we have a low carbon fuel standard. No other province in Canada has a low carbon fuel standard at this point in time. The only other jurisdiction I know of is California. And so Don is correct. You can actually, technically you apply to be a Part 3 fuel supplier. Don't tell me where they got the don't ask me where I got the names from, but that's what it is. And you can apply for that as a strata, and there's a minimum qualification. I think you have to have more than 30 suites or 5 suites or stalls, something like that. But there is a minimum qualification. But most condos will qualify. And if you apply for it, the current trading of credits, I haven't tracked it in the last quarter, but earlier this year, they were trading as high as $428 per ton. Now, I mean, it used to be sort of 200 was the goal. And all of a sudden, the last couple of years, or the last year and a half, the prices have really gone up. And this is because the whole point of a low carbon fuel standard is to lower the carbon intensity. So people who are producing fossil fuels have to lower their carbon intensities. If they don't, they have to buy credits to make up for it. And obviously the price is going up because there's a limit of how much credits are available and there's a great demand for them. Now, here's the bottom line. I calculated the value per kilowatt hour of being able to sell credits at $400 plus a ton. And it's in the order of I think about 25, 30 cents a kilowatt hour. That's a significant amount of money. And what that does is it makes just about every condo installation, if you think about it, could pay for itself fairly quickly and then pay dividends into the future if carbon prices stay high and if those programs stay long. But what it means is this is a very good mechanism to fund your condo strata infrastructure. And a lot of people don't understand that I'll just say one more thing, and Bob Sparks might weigh in here too. We were wondering when we first looked at the BC Hydro DC fast charge rates, and they came out with rates of 20, 21, 27 cents a kilowatt hour in fast charging. We said, hey, that's way too low. That's way too low. You're never going to pay back. That'll prevent private operators from installing the chargers and making money off them, because with demand charges and everything else, you'll never get your money back. But this all came up just earlier this year where we realized, oh my God, these guys are all getting low carbon fuel standard credits for their electricity. So they're not actually showing the true costs, and actually they are going to recover their costs quite handsomely. Now that has, and we brought this up at the commission, and we brought it up to our friends at BC SEA who are working with us. And I'm hoping that actually from raising this, that this has actually made this all happen. But it's a very good situation. It's a very good situation for condo owners now. There's a very good argument for putting together charging in your suite. I'll shut up.
Fascinating information, John. I'm glad you enlightened us on that. It's and I should know because I'm on the board, but I was not aware of the carbon credits that are available.
Most people aren't. It's fairly technical. I took about 6 months to study it and figure it out.
And in that 6 months of study, you just put it into a nutshell in 2 minutes. Congratulations. Is there anyone else that has questions out there? I don't see any hands up or anything like that.
Actually,
I can comment just briefly on that carbon credit one, just doing a quick look here. If you take an average person driving 25 kilometers a day in a condo, they would qualify for about $420 a ton for carbon credit. Then they would get returned about $363 a year.
So if I've got this right, so it's $420 a ton per ton for a carbon credit, and the average gas car produces 4 tons of CO2. So in theory, you could be saving about $1,600 a year. Am I even close, or am I way off the mark there?
Yeah, you're going to match basically the cost of electricity and a bit more. So yes, that's about right. Ron, there's 2 people with their hands up. Bill is first, I think, and then Greg.
I don't see any hands up at all. Did they put their hands up physically, or did they use
up on the participation list?
No, virtually.
Sure.
Can everybody hear me?
Hang on a second. Don't go anywhere. I need to see the hands up because obviously I'm missing that. And if I'm going to handle the meeting, let's get rid of participants.
Go to the participant screen, Ron, and then you can see everybody in one place.
Yeah, I don't have any hands up at all. Okay, so who did we have with their hands up? Who did you say was first, John?
Bill is first, and then Greg Merrick.
I'm sorry, can you guys hear me?
Yep.
And great. Go ahead, Bill.
Okay, good. Thank you. I super impressed Kelly and everybody else who's worked on this, both how you integrated the infrastructure part of it, and also the algorithms to balance everything, true load balancing for those IT techies out there, because you're balancing power load. But more of a practical question. I'm the president of our strata, and we're right beside a river bend. And I did not know what you guys were doing there, but that's amazing. From a practical standpoint, what is the initial cost before grants or anything like that to do what you guys did at Riverbend? That's the initial kind of common area cost. And then the second part to the question, and then I'll put myself on mute, is I make the assumption that each owner would be buying their own level 2 charger and then paying for it to be connected to the grid.
So the initial cost is quite substantial because of things like the 600 amp breaker it's about $50,000 for that breaker at Riverbend. The average cost I think is going to be about $1,000 per stall to deploy all of them. So with the Clipper Creek, the Sun Country solution, it's probably going to be like the strata would own all of the property, so it would own the EVSEs, and moving forward to a situation where you can bring your own OCPP charger. That's feasible to move where everyone does buy their own and decides which one they want, if that's what the strata wants. Because the other issue I didn't really bring up is the strata might dictate which EVSE is installed so that it all looks the same and uniform, and because it's kind of installed on common property.
I'm having some technical difficulties here. My screen is corrupted and hard to see. So John, if you could just watch and see who's got their hands up and just call them out in order, sort of take over the meeting for me.
Sure.
I can't even end the meeting properly. So if you go ahead. Yeah, you take over if you could, please.
Greg, you are next, patiently waiting. Thank you very much.
Oh, thank you. Thank you, John. So, yeah, I haven't met any of you before. Greg Merrick, I live in Toronto, and it's very late here. And I've been working with Mike Schuler for the better part of a year to take the variable grid product and work on developing it into sort of the next generation product. And I wanted to just give an overview of what the product is now and where we hope to take it. So Mike has already on the market a product which is effectively an EVEMS, which is an electric vehicle energy management system. Its purpose is to share power between a group of chargers in order to increase the density of the amount of chargers you can put on the same amount of circuitry. So just, you know, I'm sure you all understand this, but in basic concepts, before energy management was being used, every charger had to have its own breaker. So you were, you know, if you had a 5 chargers, you needed 5 40-amp breakers. With Mike's system, you could have just one 40-amp circuit running those 5 chargers. So that's the first sort of level of densification that you get when you use energy management. And that's what Kelly's been talking about. What Mike is doing is measuring the load, doing something called load sensing on the panel. And I wanted to just make the point, which I think is very important, about EVEMSs do not have to do load sensing. They can just assume that the panel is permitted to run at full load and just share the power in a more efficient way on the chargers that are attached to that panel. But if you do load sensing, you get a very important benefit, which is that that panel, which may be installed specifically for the purpose of EV charging, no longer has to be considered in the load calculation of the building. And this is a very important point that I didn't hear brought out. So if you have a building which is an older building and may have a shortage of power available in the building according to the design load of the building, you can put in effectively an unlimited number of EV chargers as long as you're load sensing the panel or load sensing the building. Because as soon as you load sense the building, all of the panels that you're using EVs for no longer have to be counted as toward the calculated load of the building. You just measure the current in the building and you allocate whatever's available outside of that current load to EV charging, and this is what Kelly's system is doing. But I didn't hear the point made that load sensing is what allows this to happen, allows the building to put in much more EV charging than would otherwise be permitted.
I guess one item I may add while you're talking that, Greg, is that we support hierarchical load sensing as well, because there may be variable throughputs on different portions of the circuits that feed the EVSEs finally. And so just sensing one point is usually, it may not be enough.
Right. So this is what Mike's system does now, is load sensing. And what we're doing, what I'm working with Mike on, is adding OCPP capability to that. So Mike's current system supports his own proprietary EVSE. The new version that we're putting out in the next, very soon now, next month or two, is agnostic for OCPP servers, chargers, as long as you are OCPP compliant. We can load manage that device. And so we're adding that capability. And then our going forward plan is to add back end support so that we can be an EVEMS that sits between a central server, which is the systems like ChargeLab and Switch, and the group of OCPP charge stations that are in the garage. So we would be sitting in the middle doing the power management, but the billing and dashboarding would all be available through another third party that you can choose. It's agnostic. You can choose anybody that you like. I did want to do a poll of the people on the call, because as we talk to companies like Switch and ChargeLab, I start to realize their business model is effectively charging each user in the strata for these services at different rates, ranging anywhere from, say, $12 a month is the lowest that you can get from Switch, up to $25, $35 a month per user per month for some of ChargeLab's products. And I see that this is effectively doubling the cost to the strata tenant, the strata owner, because the typical electrical bill for running, say, 50 kilometers a day drive is only going to be about $20 a month. So I'd like to hear what people think about, as a strata management, using a back-end system that is effectively going to double the cost of the service to their owners.
Anybody have any comments before we leave this topic?
Yeah, I can comment on that. I've looked at that, obviously, and it comes down to the size of the building and how many people there are to try to manage it. So when you have 10 people, it's quite a lot of work to manage the few people that you have charging. When you in order for it to make it worthwhile to bring it in-house. And I definitely see having it outsourced in small buildings, but in larger complexes, I do see it as something they would want to bring in-house. And especially if you're large property management, maybe it's the property management of many properties that is running one of these networks, and it's for all their properties. And then the IT requirements for them would be quite small in comparison to the number of people that are using the service.
Right. Okay, that was all I wanted to say. Thanks very much.
I'd like to weigh in on that question you had, Greg. And with every change in technology, there's always some gold rush, entrepreneurs out there that want to make a fast buck. And it's usually because people don't know much. It's new technology, so they don't know what the real costs are. And this seems to be another one of those examples. I mean, 30 years ago, it was when, we went to competitive long distance telephone services, and there'd be these companies that say, I will save you 50% and I'll share the savings with me, and that'll be my fee, and it won't cost you anything. And unfortunately, condos typically don't have the management and wherewithal to really make a good judgment. I had the same issue in our condo with some guys that were doing some fast swapping out of regular traditional lights with LED lights, and they're just light salesmen, and they're not really doing an engineered approach, and it's not really the best value. But it's tough to convince the strata otherwise. But yes, I think that's a very good point you've brought up. So all right, let's move. Don is next, then Lawrence, then Alan.
Yeah, I'll just comment further on the electric code changes for monitoring on a circuit where you don't have to consider the calculated load, the extra load of the charge stations that are monitored. That's true, but you also have to be very wary that you have enough energy available in the off-peak hours to be able to get everybody fully charged. So the analysis I've done on a number of different condos shows you usually have enough in an urban core, but if you're out further in a suburb, driving a little further, you may need a little bit more, maybe 5 or 10% more than the typical peak. And you would need to add that in if you're above the calculated load for the building and the infrastructure that's been installed already. So often that's not the case, but on occasion, particularly smaller buildings like townhouses, you do push the limit of how much energy is available overnight. You pretty much have to go through and look at your duct curve, count up the energy available each hour, see how much is available, how much is needed by the building, and do that performance calculation, and then see that there is enough energy, which may range from the equivalent of maybe half a kilowatt per stall, the charge rate, to over 1 kilowatt per stall, when the average needed may range from 1 or half a kilowatt up in a very low distance driving community like an urban core, to about up to 2 kilowatts average over the time they're home to charge. So it does take care of most of the charging. You just have to be very careful to not assume there's unlimited power available, and the circuit sizes you use are large enough to accommodate that extra through it. And we're looking at that in a couple of buildings now, but are pushed on their limit, either within 10% of their max load or actually right at the load with zero capacity left on very low distance driving scenarios. So monitoring is a solution that can really help. So kudos to Mike for inventing these concepts 12 years ago. And just to say, before we wind down, thanks to 53 participants who showed up tonight, a few have left already. I think that's a record for VEVA. And the last time we had a big crowd like this, I think was when we had a talk on batteries by Roger Stockton about 10 years ago. So it's great to see the enthusiasm. Thanks.
Okay. Don, I had a question back for you. You're mentioning that these you're running out of the capacity overnight. What's the biggest percentage of active users you've seen in a condo today? Like where are we at as far as percent of stalls with electric cars? I know in our building we have a 300 stalls. We have about a dozen electric cars. Have you seen higher densities than that?
That's probably fairly typical. We walk around a 100-car parking lot, you might see 2. Some of them installed power early and put in 100 amp circuits directly for themselves, using up all available power. But very, very few, maybe 5 to 10% at most. And we also see in the downtown a lot of empty stalls. People aren't buying cars, and they're overbuilt the parking stalls. In other areas, we see there's people parking on the street as well as filling the parking lot. So you kind of have to budget for how many cars there are in terms of how much power you need. And that's part of the calculation to figure out your performance, your demand, something that BC Hydro requires you to do in applying to the incentive program with an EV ready plan. And we've developed a lot of that, at least I have. And I'm not seeing a lot of electrical contractors doing those calculations properly and overbuilding significantly at extensive cost. And you can really reduce your cost if you can predict fairly accurately.
Yes. Okay. Thank you. Lawrence, you're next.
Great. Yeah, the idea, can you hear me okay?
Yes.
Okay. The idea of paying twice as much for your electricity in order for some third party to do the billing seems pretty ridiculous to me, given that in most cases you'll have advocates in the building who'd probably be happy as a volunteer to monitor the software and send out emails to people and then make a list and send it to the management office saying how much each owes each month, say, or every 2 months or 3 months, however you want to do it. And having someone outsourcing that at high expense just seems pretty ridiculous. You might as well keep that money in everyone's pockets instead.
Didn't Kelly, weren't you suggesting, like I know in our building, we just got a notice this week actually about charging, and what we did, I set this up 2009. I set up when we reviewed our bylaws, I made it so if anybody was charging, you just using the regular power without any special equipment, that we set a flat rate of $20 a month back then, and that, lo and behold, $20 a month for urban use of a 110 outlet, plain Jane 15 amp, is actually pretty generous still. So why don't you just go to monthly flat billing and then share the costs? That's a simple answer. Alan, you're next.
Hi, thanks. Thank you, John. I was going to just ask Kelly. Kelly, I missed part of your first area, but I'm sure it's not you. It must be other people working on all variety of this whole program. And that after you guys have a well-deserved time off, is there going to be a part of where you write down all the user manuals and the maintenance manuals so that there can be reliability and maintainability, and so that when things go wrong or when people are adding new units, there's a lot of detailed how-to information, keep things running reliably?
So our goal is to provide all that information that my team has to companies like Sun Country for them to be able to take on and support this product fully, and then I can go on and work on my next project.
Yeah, that answers my question. Good. I hope that's an important part of the whole rollout of this kind of program, because fancy material need pretty fancy maintenance and a lot of attention to keep it working well.
Terrific. I don't see any more hands up. Ron, back to you. Are you? Oh, unmute. Uh-oh. You still have technical?
I was just going to say, Kelly, why didn't you say that open source software usually comes without any warranties of any kind?
Well, because I may be providing it open source, so other people can use it without fear of being sued by BCIT for them taking and using this.
Yeah,
software.
okay, but that's all right. That's only part of the story. Yeah.
Yeah. So if you want to use it to advance your product faster, you can take any bits and pieces out of my software and then provide a warranty onto it as a commercial service.
I would imagine as open source, it's sort of like Linux. A lot of people, some people make money off of Linux, but they make it as being a consultant, how to set it up, how to maintain it, that sort of thing. Is that how you see the OCPP system? Like that's how businesses will interact with it, because they will say, yeah, we'll set it up for you, we'll configure it, and we can monitor and support it after the fact.
There's many different models, and like one is that these buildings would install their own network and run it just like a Charge Labs or Switch or whatever, but just for themselves. But there's also the idea that you have service providers that will just run the server directly for you, and then and either charge you like a flat monthly fee for running the service, like for hosting your service, versus trying to charge customers for their service.
Don has his hand up. Don, would you like to ask your question?
Hi, yeah. So I'm a kind of a duffer, a little intimidated with all the smart electricians in the room here tonight, but hopefully this question will make some sense and maybe give some clarity for those of us who aren't experts on how it works. So Kelly, when I looked at your presentation, I was able to understand all of the metering of all of the lines so that you're not blowing the breaker, but I didn't really quite understand what the switching or the feedback mechanism to control the power usage of each of those EVSEs. Like you said, you control them in 25% clumps. But what is the mechanism for metering the power, and what time scale does it work on? I was kind of surprised you were talking about minutes, not seconds. And how does it work so that the main breaker doesn't get overloaded if a bunch of cars quickly plug in? Presumably it has to shut down the power on all of those quite quickly so that you don't get a surge. And so how does that switching work? And I also wanted to know, could you set up the system? You talked about the problem of if you take somebody's power down to zero, the car may not boot up again when you resupply the electricity. Can you limit those circuits so that they would always provide 4 amps or something, so that the car would stay actively charging at a kind of a trickle level, and all 100 stalls or whatever you're using will be supplied with a minimum amount of electricity to keep everybody engaged?
Yeah, so there's a bunch of questions. So we'll start with the minimum amount. So that was one of our defects that we found with some cars. So we would set their profile up saying that they must get 8 amps as a minimum all the time. And then as long as we could do that, we were happy, if the software would be happy. But there are cases where maybe there is a critical power shortage and everybody needs to get shut off. So we would have to override that minimum and say, sorry, we've tried turning everybody else down and we're still over our limit. You have to your car will get shut off as well. And I know that might mean that it might not come back up. So we do try to make that happen so that the cars always get power. The setup that I have for Riverbend and for BCIT means there's always at least 8 amps of power available for charging. So we don't really have a reason to take them down to 0. So the way the software works is that when you plug in a car, the car says I want power through the EVSE, but the EVSE is set to 0 amps, and the software says, oh, there's a car that's arrived at this charging station, and if authentication is required, they would then have to go to their phone or to tap an RFID card, and the charging station would then know, or the software would know, that we have an identity, we know who this person is, they're allowed to charge, so we will activate that charger. And the local controller, the way it works is really interesting, that it would keep monitoring the power every 10 seconds on the entire network. And every 10 seconds, it would make a new move. It would say, oh, is there anybody that I need to turn on or turn up? If there isn't anybody that needs to be turned on or turned up, it looks and says, do I need to turn anybody down? And it does that every 10 seconds, and it just keeps going. If it decides it tries to turn someone up, and then it looks at the power and says, oh, we went over our power limit by 1 amp or 2 amps, it says, that's not acceptable. Let's roll that operation back. For whatever reason, it went over our limit, because of 3-phase math of power systems can do that, becoming unbalanced. And it will roll that person back. So if we move them up to 24 amps, it'll say, don't put them back to 16 amps, and don't offer them 24 amps for the next 2 minutes. Let's see if anything else happens on the network. And so that's how it runs, and it is always monitoring to keep things in control. The Teslas don't like that too much. If you raise the power and lower the power too often, being really twitchy like that, they will get stuck at a lower setting and not take all the power that you offer them. So that was one of the reasons that we wanted to move to a cloud-based solution, which is not thinking in seconds, but we're thinking about what should the setting be for these chargers for the next 30 minutes if nobody shows up and no one finishes charging. And so in the cloud, it's like, oh yeah, here's the new settings. We've worked it all out in advance. Now let's go tell the chargers, here's what the rate you should be at, and just run. If 2 minutes later someone shows up and plugs in and says, oh, okay, the plan that we made 2 minutes ago isn't any good anymore. Let's make a new plan to start this new guy and see how he fits into the overall plan. Did I miss anything, Don?
No, that was very clear. Thank you. And I'll just summarize for us non-technical guys. What I didn't realize is, of course, when you plug into that charger, you don't get power right away. Your system has plenty of time to think it through and decide what to give me before it starts me up. And that makes it easier to manage. Yeah.
Right. Yeah. It's trying to be proactive in planning versus reactive, but it does have a reactive component that it will react to things not going the way it thought it should.
And of course, all of this monitoring is done through algorithms. There's nobody looking at the system and saying, oh, I'm going to go up to 16 on this one, or it's all algorithms that are programmed to.
Yeah, it's all algorithms and models of how these things are supposed to operate and the way they interact together.
Thank you.
Can I chime in about communication between the car and the charger?
Sure.
So kind of in a mechanistic sense, you can tell, I guess you talk to the charger with the OCP protocol, but then the charger has a square wave over the control pilot pin on the J1772 connector that tells the car how many amps that charger is good for. And so I imagine as the charger gets new instructions, it changes the pulse width modulation signal on that square wave over the CP pin. And then the car says, oh, okay, I can take more, or I need to throttle back and take less.
That's correct.
Hey, Kelly, I'll just jump in quick here. I kind of like the idea that there's an algorithm. My name's Alan. So instead of saying, hey, Google or hey, Siri, I can imagine each car saying, hey, Al, give me some power. And then the algorithm reacts. I like that.
Algorithm.
Yeah. The other part of the process of the charging is we end up in a state where it's called waiting for the EVSE to give power. The EVSE will then say, yes, you can have 8 amps or 16 amps, and it transitions to charging mode. When the car decides, I don't want any more power anymore, and it goes to this mode where it says suspended by the vehicle or suspended by EV. And it can stay in that mode for all night. And maybe it will say, I want power again at 6:30 in the morning when you want to preheat your vehicle. A lot of OCPP chargers would actually finish the session when the car stopped charging at 2 a.m. when it thought it was full, and then would not be able to start again to automatically preheat. You would have to start another session in the morning to do a preheat. The system that I put together for Sun Country is that it will stay in that waiting for EV mode all night long, and your charging session will actually appear that it lasted the entire time until you unplug. But you do get if you have emails enabled, you would get an email 5 minutes after your car stopped charging and didn't ask for any more power. So if when the Leaf is just about done, it will go down to 0 amps, and then it'll sit there for a couple minutes, and then it'll start charging again to topping up and then stop. And you can see a couple little bumps of it asking for power. So in that period, it wouldn't be sending out emails to say that your car finished. It would wait until there was like a 5-minute period where your car said it didn't want power, and it didn't ask for power again in that 5-minute window.
I'm just going to jump in because Ron's not seeing. We have a couple of hands up, so I'll just take charge here. And first hand up is Harvey. Do you want to go ahead, Harvey?
Yeah. First of all, I think this is a really incredible meeting, and I'm part of a Strata Council up at Whistler, and the demands of power in Whistler are mostly for visitors that are spending 5 days, 3 days, where they're charging their car, and then they're going to leave their car for the length of period of time that they're at their vacation rental. So there doesn't really need a lot of power compared to people that are commuting every single day. What's the minimum amount of power that would be required for 139 stalls, especially when only, let's say, 5% of the stalls would be used by permanent residents that might need to commute. And even if they did commute, it wouldn't be for any real major length of time, because if they're living in Whistler, they're usually either commuting throughout Whistler or somewhere local as far away as maybe Squamish or Pemberton, where your commute may be only 40 or 50 kilometers, maybe a little more. But we're trying to get some EV chargers in our complex, and we know that our capability of providing a lot of power is extremely limited, and we want to get in some chargers, but how many chargers can actually put in with this EV management system called the OCPP? And the other question I have, I'm a very good friend of Kent Rathwell, the one who's the CEO of Sun Country Highway, and he would know a lot about this, working with you as well, Kelly. Is that correct?
Yeah. Kent talks to me every couple of days, see how I'm doing, and he's really itching to get selling this system.
So Kent is providing your system to different condo buildings through your software.
Yeah, he will. He has one customer that he's got system half deployed, and so running without the management system. And by the end of December, as I get better, he'll be able to start deploying this.
Now, the other question I have is, I'm not sure if you know PBX in Squamish, that engineering firm.
No.
Anyway, they're the ones that did the evaluation of our electrical to see if we have any power available for EV chargers. But could this company work with a company like yours to be able to have an EV management system, or would they just go directly through Kent?
They could go directly through Kent.
Okay, that's great, because I talk to Kent on a regular basis, and he was actually my co-pilot when we did a cross-continent tour. We set a world record from St. John's, Newfoundland to Mile Zero. He was my co-pilot.
Yeah. So Don Chandler would be the correct guy to talk to about how much energy you guys would need in your building. I don't know if he can calculate that in his head at this time, but he's the guy that can do it.
And Don Chandler is next hand up. So let's go to you, Don.
Thank you very much.
I want to answer Harvey's question directly because it's not a standard condo with people just commuting to work. The distances are, you'd have to go through all the details to predict it. But back to the other previous question, one thing Dingham mentioned is that the communication between the charge station and the car is controlled by the protocol J1772. And it's pretty much one way where it just sends a signal to the car saying, here's how much power you have. And the car is required to obey that signal. So the minimum being 6 amps is why you can't go down to 4 amps. And in the early days, some of the cars didn't behave properly and they thought 6 was 5.9 and didn't respond to it. So everybody pushed it up to 8 amps. That's pretty much resolved now by most of the cars in the market. So that's where it's at. But in Kelly's description, he kind of alluded to the idea that he would share power equally or semi-equally to each of the cars. But I know his algorithm is a little bit smarter than that, and he'd say, oh, this guy is higher priority, he gets a bit more, this guy can wait. But he's still sharing 2 or 3 cars or 4 cars simultaneously. When he has 10 cars on the circuit all waiting, somebody has to wait in line, kind of a round robin type, or in a musical chairs game. Those cars that are waiting are going to have to be paused. But if you have an algorithm where you say, well, the first person in gets the power, and then the second, and the third, and maybe after the 4th car is in, the 5th, 6th, 7th car just have to wait in line. If the first or second car never ends their session because they know they have to precondition their car at 6 a.m. before they go to work, they'll stay in a pause state all night until they turn on their heater or air conditioner in the morning. And that would prevent other people. So those, with the first in, first out algorithm, you can charge an unlimited number of cars in the circuit, but any one car could hang it up and make everybody wait just by going to sleep for a few hours. So algorithms like Kelly works around that, tries to get equal energy shared, and it should work out pretty well. For Harvey's question, I think we sent you a proposal to how to do it. We went with a local firm, that's fine. They should be able to calculate the performance, how much you need, and whether or not you can do it. How much people drive is not very much, but some people commute to Squamish or Pemberton or back and forth. Those people are going to have, and how many there are in each one, will all have to be added up. It's part of the EV Ready plan work that is done that the BC Hydro requires to estimate that. I suspect just roughly you're going to need, I can't guess, can't do it in my head. It's just such an oddball. But Chuck Lear, the engineering firm who's done it for you, they should have been able to lay that out for you. It's part of the requirements that they have to calculate in the EV Ready plan.
And would they know about these new open charge point protocols? I mean, a good electrical company, that they're actually the ones that put in the chargers in the Whistler parking lots. They put in 14 charge point chargers. They
might know about the protocol, the USPP protocol and smart chargers. They may be familiar with them. It's a bit more esoteric than just putting in a dumb charger in a public charge station. So they might not know the esoterics. The OCPP is just a protocol of how they communicate. It kind of dictates the language you speak, but not the story you tell. So in Kelly's story, he's doing some very smart things. I know Mike's using artificial intelligence to do this. And as our other companies we see are getting very, very smart about how they manage the power. Some are enabling priorities so people can have priorities. And I'm sure that'll be a business model in the future. So there's lots of different ways this can be managed, and you'll see different business models coming out. They'll get very, very smart. And some will try to minimize power, some fast charging. It gets quite sophisticated.
Okay, we're pushing 9 o'clock here now. I think we should give it over to Kelly to see if he has any last words or summary or as we head off. And then maybe if any of the other experts want to say a last word, we give them a chance as well.
Yeah, so it's definitely where we're heading. I'm not the only person out there looking at this stuff. I want to make sure that this technology gets deployed to as many different companies so everyone can provide the same level of energy management that I've been working on for the last 5 years. And I know Add Energy Flow has some of this built into their existing product line, and we've used it in a previous project. So it's definitely getting out there. So I think this is looking really great for the future of us, and BC is kind of leading the way in this area.